Ladies and gentlemen, we obviously have a bit of a change of venue here. That's because for the next unit, well, really the next couple of units, I end up having a few PowerPoint presentations that I end up using. So I'm going to upload the PowerPoint presentation so you guys can have access to it, and I'm going to, of course, go through it and talk about it. You guys will also, of course, have a copy of your book. Right now, we're going to be dealing with the physical properties of matter. So we're going to be looking at some of the rules, the physics, behind the different states of matter, why things are the way they are. Like up until now, we've been talking about moles and grams and particles, and we've been turning one thing into another, doing a lot of math. Now we're going to talk about more theory. What's happening? Why is it happening? What does all this stuff mean? Like, where's it come from? So we're going to move forward a bit. The first couple of pages of your book are sort of a little exercise for you to do, sort of an introduction to the unit. But we're going to start off with this. This is a basic idea behind the structure of matter. So right at the top here, we've got all matter, okay? And then what we see is that matter is sort of divided up into categories. And the reason we do that is because trying to talk about all matter at once, that's too much stuff. Realistically, we need to break that down in some way. So to that end, we break down matter into some categories. The first category is, of course, pure substances. The second category is sort of its opposite, mixtures. Each of these is then further divided up. We've been talking about pure substances pretty much exclusively up until this point, right? In all of our stoichiometry, we were only talking about materials that existed as elements or compounds. So, stuff like oxygen, gold, iron, or salt, sugar, those kind of things. And up until now, we've been doing a lot of chemistry. We've been doing a chemical change. We'll talk about more about that in a second, where we've been going from elements to compounds, or compounds to elements, aka synthesis or decomposition reactions, if you remember what those are. But now we're going to be doing something a little bit different. Now we're also going to be talking a bit about mixtures. So mixtures, of course, are going to be dealing with heterogeneous and homogeneous. So dirt, blood, milk versus soda, gasoline, air. Seems like quite the weird distinction, doesn't it? So a little bit of pictures can help. A heterogeneous mixture is where you've got like two or more things and they're clearly separated from each other, right? This is the red-blue zone and this is the blue-green zone. A homogeneous mixture is when they're all mixed together and they're sort of random. So if I reach in and grab one, I don't know what I'm going to get. So for example, this one over here, a classic example of this, oil and water, right? Over here we've got, of course, our pure substances that are just an element, so everything is the same. Over here, everything is the same, but they're molecules, they're compounds, they're multiple things put together. All right, that shouldn't be too big of a surprise, I don't think. These categories make things easier for us. That's why we have categories. The purpose of categories is to make it so that way everything is simplified. Rather than have to remember every single piece of matter that exists, you remember categories. Moving on with this, we see that the properties of a substance are the set of traits by which a substance is recognized. So we divide these traits into groups to make it easier to understand them. So that's what we're kind of dealing with here, right? We're going to be dealing with these properties, both physical and chemical, because it's the way that we identify matter, right? We look at something and we go, oh, yeah, that must be iron. How do we know that's iron? Because we look at it and we have properties, traits that let us know that it's iron. So we have two broad groups that we're going to be using in order to identify materials, okay? We're going to be talking about their physical properties and their chemical properties, okay? So physical properties are traits that can be observed by examining the substance. So I pick up a particular object and I look at it, for example, my beaker mug, and I go, it's transparent and solid. These are traits that I can observe just by examining the object. Chemical properties are a little less clear, though. In order for us to get chemical properties, we have to observe chemical properties by reacting it with something. So I can't tell about the chemical properties of this without doing some chemistry to it. I have to combine it with some chemicals and see what happens. So that's a little different than a physical property. A physical property you can observe just by, looking at it or touching it or smelling it or tasting it, something like that. Not so much with the chemical properties. So here are some examples of physical properties, right? You guys have got some blanks to fill in here. You got color, odor, taste, density, melting and boiling point, electric conductivity, malleability, ductile, or luster. All of these especially these last ones, are probably ones that you're not as familiar with. So electrically conductive, able to carry current. That can also be thermally conductive, which means the ability to carry heat, but that's another matter. Malleable, able to be shaped in some way. Ductile, able to be pulled into wires. Shiny is the ability of it to, well, shine, right? Luster's the fancy way to say shiny. These are chemical properties. I got a nice picture for this one. Chemical properties are curious. Many of them you're familiar with, like toxicity. Is it poisonous, right? That's a property. Not one you want to test personally, mind you. Oxidation states, you won't learn about that until grade 12. Heat of combustion, you kind of already know this. That's how much energy you release from the object when you light it on fire. Then what do we have? Well, oxidation, chemical stability. You know what chemical stability is, realistically. That's not a big surprise. Flammability. Flammability. That's so complicated. I wonder what that could be. The ability to burn. Coordination number down here, we don't deal with that. Reactivity, that's very similar to chemical stability. In many ways, it's kind of the exact opposite, right? Like if something's chemically stable, it's not very reactive. And if something is very reactive, it's not very stable. Possible chemical bonds and enthalpy of formation. Again, some very complicated terminology here, some words that you're probably not familiar with. Now, we can divide these properties into categories further. The reason why scientists use categories is because they make everything easier. Not like super easy, but easier, because it's always easier to remember a category than individual things. So in this case here, right, properties can be broken down into extensive, which means that it changes depending on the amount of substance. More material, the property changes. Now, this is a binary category, so that means that there is an opposite to this. The opposite to this is intensive. Intensive here means that it doesn't matter how much material you have, it's exactly the same. So, for example, it doesn't matter if I have a huge mountain of paper or like one piece of paper, they're both still flammable. Doesn't change anything. Ah, yes, bit of joking around here with some chemistry stuff. By adding water to an equal mass of aqueous solution of H2O, you cause the water to double in volume. Ooh, look at that. You add more water, you get more water. Who would have guessed? So here are some examples of extensive and intensive properties. So the intensive properties, remember, don't change no matter how much you have. So the boiling point, right? Like if I have a glass of water or I've got a lake of water, they both boil at the same temperature. Color. Doesn't matter if I've got like a single chair or 20 chairs, they're all still the same color. Temperature. More stuff doesn't make it hotter or colder, it just means there's more of it. Similar with shininess and hardness, right? Diamond isn't any less hard when there's less of it. Compare that to stuff like volume, mass, size, weight, and length. Obviously, those will change depending on how much you've got, right? If I physically have more water, I will have a mass of water because it's heavier. So extensive properties and intensive properties, they're not like super critical. If like realistically, anybody who looks at this can generally tell which things are going to change with the amount versus which things won't. You're dealing with properties of one type versus properties of another type. It's not a big surprise, right? Like, not really. These ones at the bottom are all really self-explanatory. They're really obvious. All right, but we're going to get a little more complicated, right? So in chemistry, a substance will often change, sometimes violently, aka we get a kaboom. To keep track of the changes, chemists use the same two categories since they're familiar. What do I mean by that? Well, take a look. A physical change is a change that doesn't create or don't create new substances, changes. Chemical changes are changes that do create new substances. So what we're talking about here, right, is that we're going to be changing our different materials in some way, right? We've talked about up until now that there are materials and they have properties and they exist and we're done. But now I'm saying we're going to change them. We're going to put things together. They're going to become something different. So what would that look like? What does that do? Well, because physical and chemical already existed as categories, right, we decided just to sort of continue working with that idea. So as we can see here, we're going to create new substances if it's chemical, and we won't create new substances if it's physical. So that's sort of our approach. So here are some physical changes, right? Like if I break glass, I don't make anything new. I still have glass. I just, have broken glass. If I boil water or melt ice or crush a can, that's not going to change what I have, right? If I boil water, I still have water. It's just a gas now. If I dissolve sugar in water, I don't magically make the sugar disappear. I just have sugar in the water. So the two of them are mixed together, but I can separate them out. Chopping wood, mixing different types of marbles, sublimation of dry ice. Yeah, that one's super obvious. Sublimation, we'll talk about that a little later on in this particular unit, but basically that's the ability of something to turn from a solid to a gas. So what we're seeing here is that physical changes, right, aren't creating anything new. All of this stuff started and then is continuing. There's no surprises here, right? There's no, oh, look, hey, we got something completely new. No, we don't have any of that. Okay? Now, chemical changes, these make new things. Look at these ones. Rusting metal, combusting wood, metabolizing food. To be honest, these three are kind of the same thing in a lot of ways. What? Why are they the same thing? Rusting iron is really the same as combustion. It's just slow. If something is rusting, it will be oxidizing. It will gain oxygen. So iron, when it rusts, turns into iron oxide, either iron 2 oxide or iron 3 oxide. You know the difference between them, of course. But it's just gaining oxygen. Well, that's what combustion is. The difference is combustion does it very, very fast. Metabolism does it very slowly compared to combustion, but this is why we say you're burning calories, because you kind of are doing combustion. Yeah, it's kind of weird. You may remember that we ended up talking about the combustion of wood was something like CXHY plus O2 goes to make H2O plus CO2. Well, it turns out that metabolism is almost the same thing. The only difference is that we put an extra O in here, OZ, because it turns out that sugar, which is the main thing we metabolize, has got an oxygen in it. Yeah, so the rest of combustion is still the same, right? That's why we need to breathe in oxygen and breathe out carbon dioxide. It's also why you have to pee. All that water has to go somewhere. So rust basically does the same thing, except that instead of dealing with some kind of carbon compound, right, instead of CXHY and then O in the case of metabolism, instead of dealing with some kind of carbon compound, here, let's put it over here, CXHYOZ plus O2 goes to make CO2 plus H2O. This one here does something like, say, a metal. So we'll just say M for metal. And we don't know how many there are, but we're going to add some oxygen to it, and we're going to get some kind of metal oxide. And we don't know exactly what it's going to be. It's the only one that looks different from the other two, and yet it's kind of basically the same thing. Add oxygen until it changes chemistry. And all of this is about changing the chemistry. We're making new materials. If you remember, going back a bit, whoa, this one. It says here, a chemical change goes from elements to compounds, right? Pure substances. So we go from like just one thing to things combined together. Well, take a look at these chemical equations that I've written on the board that are kind of obscured right now. There we go. We can see them a little better. I've got an element of metal plus oxygen gas makes a compound. I've got a compound plus another compound makes two other compounds. Same thing here. So all of these are sort of fitting the same basic pattern. We have been talking all of this time about chemical changes without really calling them chemical changes. We just said they're chemistry and called it a day. We can also see that physical changes go from pure substances to mixtures. Now, that's maybe not quite as true, but it's a useful little thing. I mean, if we take a look at our list here of physical changes, next slide. Right, this okay, two pure substances, sugar and water, and then I mix them together, so I made a mixture of some form. Okay, that one checks out, but what about the others? Mixing red and green marbles? Well, I mean, I guess I had two pure substances, one red marbles, one green marbles. I mixed them together. Chopping wood, that one's a little bit tricky to do in this context. I mean, I went from one piece of lumber to two pieces of lumber. I didn't really make a pure substance impure. So I don't think it totally works. Not for certain kinds of changes. Mixing kinds of changes, yes, but dividing changes, crushing, shredding, chopping, cracking, those ones, melting, boiling, those ones it doesn't really apply to. But either way, it's a good little like rule of thumb we can use to try and explain things. Anyway, let's continue here. Cooking an egg and baking a cake, those are chemical changes because once you're done, you can't get them back, right? You denature the proteins in the case of cooking an egg. There's a word for people in biology. In the case of baking a cake, you end up doing a whole host of different reactions. A lot of acid-base chemistry, actually. Electroplating, that's how you get metal on top of other metal. So that's how you get like a gold ring that's not actually gold. It's just normal metal that's got like a little bit of shiny golden color wrapped around the outside. Rotting a banana, that's something decaying. To be honest, a banana rotting is very similar to metabolism. It's just the metabolism done by things that are so small we can't see them, right? Like little bacteria and stuff. Vinegar and baking soda mixed together, that's an acid-base reaction. Fireworks, best type of chemistry because it burns and changes color. That is obviously going to be chemistry. And then a chemical battery, which is very important, right? All of our cell phones rely on that thing. Without a chemical battery, we're not getting anywhere. So these are examples of chemical changes because when we're done, what we started with is gone. We've replaced it with something new. So we've gone from an element to a compound or compound to an element. Most of the time we turn into more complicated compounds. All right. Changes in energy. In order for something to change, either chemically or physically, there has to be a change in energy, right? What am I saying? In order for any of these things or these things to happen, energy is required. Stuff doesn't just like, ta-da, something has to put in the work. So what do we look at here? Well, usually chemical changes use more energy, but it does depend on the scale, right? Like if I put 2 drops of baking soda and 2 drops of vinegar together in a beaker, yes, that is a chemical change, and that will be in theory, take more energy than, say, chopping down a tree. But chopping down a tree is a lot more work because trees are really big. If I had to mix together as much baking soda and vinegar as I needed to chop down a tree, it would take a lot more energy to do that, just because the chemical changes require more. So, oh, yeah, here we go. Hurricane's coming. I will use my super breath to freeze the surface of the ocean and stop it in its tracks. I wonder how much energy it takes to freeze the entire Gulf of Mexico using only the compressed air at the surface. Atmosphere suddenly disappears. Everyone dead but Superman. Superman eases sorrows by printing daily papers. It takes a lot of energy to turn all of that water into ice. But we'll talk more about that a little later. Right now, we're going to talk about the absorption of energy. So a reaction that absorbs or uses energy is said to be endothermic. This is a fancy word here, okay, because it uses Latin. Thermic just means heat. Endo means in. So heat is going in. That's what you see here, right? The heat is going into this beaker full of stuff. Physical endothermic reactions would be stuff like melting ice or evaporating water. Chemical would be stuff like making hydrogen gas and oxygen gas from water. The way you do that is that you take water and you have to pass electricity through the water. And as the electricity goes zapping back and forth, it separates out the hydrogen and the oxygen. If you don't put energy in the form of electricity, nothing happens, right? That's why, for example, the waters in the ocean don't spontaneously turn into flammable oxygen. Because, fun fact, that would be bad. I know, shocking, right? So, we've got another binary here because there's also the release of energy. See, the energy is coming out of this particular thing. And when we release the energy, we call that exothermic. Thermic, again, means heat. Exo means out. So out heat, right? Endo, in heat. Exo, out heat. So when the heat is coming out, that means that, well, it's losing heat. So, for example, that would be if you freeze water or you crystallize a solid in some way. Chemically, that would be stuff like Burning wood. Fun fact, burning wood releases heat. I bet you didn't know that. I know, I know. Here's the weird thing though. This always messes with people. If the heat is coming out of the material, that means that it is losing energy. Okay, why is that weird? Because, and here's the kicker, if we burn wood, the heat, the energy leaves the wood, so overall the wood gets colder. Not right away, and not for anything that touches it, right? The heat is leaving, it's going out, which means that for as far as the wood is concerned, it's like sweating a lot and it's letting all the heat out. Anything else that gets close to the wood feels that heat, but the wood itself is losing it. It's a weird way to think of it. We're used to thinking of cold as like its own thing, right? Like, oh yeah, feel how cold that door is. You don't actually feel how cold something is. What you're feeling is the heat of your body being sucked away by the thing. This is always a weird one when you think about when it comes to, say, metal. I've got here my keys. These keys are, of course, metal. So metal always feels cool to the touch. Why? Because the metal is endothermic. The metal is sucking up all the heat from my body. As the heat leaves my body, I feel colder because I'm losing heat. The key feels warmer as a result. Not at first, it takes time for it to heat up after it sucks up enough heat from me. But that means that I, when I pick up the key, feel that the key is cold because it's sucking heat out of me. But the key thinks that I feel hot because I'm giving heat out like crazy. Basically, I'm exothermic, like all humans. But the key, being made of metal, is endothermic, like pretty much all metal. So it's one of those weird things about how this kind of stuff works. It's all about the way you look at it, the perspective. And it's so strange. And yet, it kind of makes sense when you start to piece it together. All right. We've got a few more terms we got to define, and then I'll turn you guys loose. Compressibility is one of the ones we need to know. This is the ability of particles to move closer together, right? So, for example, when you guys would be sitting in a classroom during this time, we'd be pretty spaced out, right? 2 meters apart. Well, if I were to tell all of you guys to get shoved in the corner, you could. There's enough room for it, like it would be, very unsafe, but I could tell you to do it, and you could do it because there is space between everything. However, just because you can doesn't mean you want to. So most materials aren't very compressible on their own. Diffusion is kind of the opposite. Diffusion is the ability for particles to move through another substance. So usually for this one, I'll do a little demonstration, and I'll get like an air freshener, and I'll put it in one corner of the room, and I'll ask everybody to put their hands up when they smell it. The odor, the scent from the air freshener will slowly diffuse through the room. It's like an invisible ghost that's just sneaking through everything. The fact that it's invisible doesn't mean that you can't detect it. That's what the nose is for. But because the air allows this diffusion, it means that we can pick up the scent. Now, anybody who's ever smelt anything will tell you that there is still a difference between smelling something far away and getting up right close and personal. Similar, I'm pretty sure none of you guys can smell any food from like Toronto right now. So there must be a limit to how far odor, scents can reach through the air. And there is, and we will talk about that, although not entirely in this unit. That's kind of more of a solutions unit, but more on that later. Density is another term that we're going to need to know, right? The density of an object is a physical property of matter, so it's not a chemical property. All substances have a specific, unique density, all of them, right? It doesn't matter if I find a hunk of iron on Earth, or I go to Jupiter, or I go to Mars, it should have the same density, in theory. Density is defined as the mass of one unit volume of a substance. Put another way, density is the mass divided by the volume. Generally, we use something like grams per liter, or really more likely, grams per milliliter. Density can help us to determine whether something will sink or float, because if it's less dense, it floats, and if it's more dense, it sinks. When I say less dense, I mean less dense than water, right? So let's pretend, oh, why are we pretending? Water's got a density of 1. Do I have water here? No, I don't have water here. Water's got a density of 1. If I put water in the bottom of the glass here, and I put something on top of water that's got a density of half, so it's half the density, it will float on top. Oil is the great example of this. Now, this is not a huge surprise. So, okay, here we go. Aluminum has a density of 2.7. 2.7. Is that more or less than 1? Pretty sure it's more, so aluminum will sink. I don't think anyone's surprised by that. Yeah, metal sinks. Shock. Look at neon. Neon doesn't sink. Neon is actually pretty light. It floats. So if you had neon, it would float on top of the water. Oh wait, neon's a gas. I don't think anyone is surprised that a gas floats on top of water. That's why, air is here and water's down there, because that's how that works. All right, well, give these examples a try. I'm going to do them too. And obviously I'd like you guys to, do it as practice, so make sure that you guys give the full attempt. The density of material is equal to density, this is a symbol for it, is equal to mass over volume. So we've got 35 liters of aluminum. Okay, 35 liters of aluminum. And it's asking us, what is the mass? So the mass we don't know, but we do know the density, which is 2.7. So this is going to be a little bit of algebra, right? We're going to have to multiply both sides by 35. Now, unfortunately, I didn't bring a calculator. Fortunately, I'm just going to cheat and grab one. A little bit of movie magic. We take out our trusty calculator, and we're going to go 2.7 times 35 equals 94.5. 94.5 grams. So we have 94.5 grams of aluminum in 35 liters of aluminum. That seems like an awful lot, to be honest. Makes me wonder. Well, let's do the next one. What is the volume of 1 mole of neon gas at 25 degrees Celsius and 101.3 kilopascals? 1 mole? Oh no, we'll have to do a conversion. It's a good thing we've just had like 1 trillion hours of practice with that. So 1 mole of neon, Ne, we're going to have to turn that into grams of neon. 1 mole is equal to how many grams? The only problem is I need a periodic table, and I do not have one. But thankfully, there's a periodic table on the wall. So I come over here, I take a quick look. It says that it is 20.8. 20.18 grams. So if I have 1 mole, I really have 20.18 grams of neon. So now that I have my grams, now I can do the actual calculation. I want to know the volume. So once again, my equation is going to be rho equals m over v. Yeah, that's the Greek letter rho. That's what they use for density. Why? Well, the Greeks kind of figured out an awful lot of stuff around density, but that's not the real reason. The real reason they use the Greek letters is because a lot of science guys are nerds, and they also know Greek. So we know the density is 0.825. And we know the mass, in this case, is 20.18, and we want to find the volume. Now, let's change colors here. We've been using blue too much. I want to get this V up on the other side. So I'm going to multiply both sides by V. That'll cancel out the V down here. So I'm going to erase this one, and I erase this one. Then I got to get that V by itself. So I'm just going to divide this by 0.825 on both sides. Those two cancel. And I plug that all into my trusty calculator, and I get 20.18 divided by 0.825. I get 24.46. Volume equals 24.46 liters. There we go. Density calculations are pretty easy, especially compared to all the other stuff that we've done so far. Usually students struggle to really grasp density. You guys were introduced to it in grade 7. And for the most part, everyone sort of spends their first little bit going like, how does this work? What does it do? Just remember that density is trying to take a measure of like how much mass, right, how much stuff is in a given volume. Is there a lot of stuff in a small space? Well, then it's very dense. Is there a lot of space but not a lot of stuff? Then it's very not dense or very light. And that's kind of what we're looking at here. Compared to the stoichiometry questions you guys have already done, this stuff is pretty easy, right? At this point, I'm going to turn you guys loose, let you guys do some practice. This is quite a lot of material. This is what we call front loading. We're giving you lots of information at the start so you guys can give it a try and sort of start to get a handle on what we're talking about. All of these different properties and changes, we're going to see these more and more as we work through the various pages going forward. These are just some broad categories to help us understand what is going on and what it means. But either way, here we are. We're done our first video of the next unit. I'd like to know what you guys think of this format, if this really kind of works. I'm not sure if the lighting is good or anything else. But yeah, feel free to leave some comments. Let me know. Maybe at some point, eventually, I will get a good camera. Maybe. They're in short supply these days. What can I say? But on the plus side, at least, we are still getting good quality sound. So I will see you guys next time.